Hassler here. I am back for the second part of lesson 7.3. We are breaking this up over two parts because it is a lot of information to take in. And so I'm on the next page, just extending the 7.3 lesson. And so problem 8 says complete the table of values for f of x equals x squared, g of x equals 3x squared, and h of x equals 1/3 x squared, and then graph. And so if you recall, f of x equals x squared is just that parent function, right? So I'm going to do negative 3 squared, that's 9, and negative 2 squared, that's 4, and negative 1 squared is 1, 0, 1, 4, 9. Okay. Let's just go ahead and graph that. So we've got negative 3, 9. So this axis is going by ones, this y-axis. So that feels nice. You'll be graphing this parent function so often that you will become a pro at graphing. I'm just going to go ahead and label that since we're going to have some, two other graphs on here. All right. And so now I have to find the table of values for the g function. So again, I'm going to go ahead and I'm still substituting in these x values. I'm going to put them into this x function. And so let's see, I have 3 times negative 3 squared. I'm going to do that exponent first. Negative 3 squared is 9, and 9 times 3 is 27. Right? So same idea. If I put negative 2 in, negative 2 squared is 4. I'm going to multiply that by 3, I get 12. And so it turns out that I'm just going to be multiplying each of the parent function y values by 3. 0 times 3 is 0. 1 times 3 is 3. 12, 27. This seems reasonable. I still have this 0, 0 as my vertex. I still get these repeating y values. Okay. I'm going to go ahead and graph that. So at negative 3, we had 27. Okay, well, that's off my grid. At negative 2, I have 12. All right, I can graph that one. At negative 1, I have 3. I still have 0, 0. At 1, I have 3, and at 2, I have 12. Interesting. So in the last lesson, we talked about shifting up or shifting down. We talked about shifting left or shifting right. It does not feel like I shifted, like I did not move up, down, left, or right. I know that because I still have this vertex at 0, 0, so that didn't change. But this graph looks like it's skinnier, right? It's narrower. It's more narrow than the red graph, the parent function. It kind of looks to me like this y value at 1 got stretched up to a y value of 3, and this y value of 1 got stretched up to a y value of 3. This y value of 2 got stretched up to, this y value of 4 got stretched up to a y value of 12. And so it really feels like there's this pulling that's happening. My graph is being pulled in this upward direction. It's not shifting up. It's just the vertex is still being held down in the same spot, but the rest of the graph is being stretched up or pulled upwards. Okay. So let's see what happens when we fill out the table for h. All right, let's see. I'll do that in green, purple. All right, so h of x says that I'm going to square the number x squared. So we'll do negative 3 squared. Negative 3 squared is 9. And then I multiply by 1/3. All right, so 1/3 times 9 is 3. Okay. And I'm going to do negative 2 squared. That's 4. So I've got 1/3 times 4. Okay, well, I'll just write that as 4/3. Right, I think that would be 1 and 1/3, but we use it in proper fractions. So what it looks like is I'm taking the original y value and I'm going to divide it by 3, or I'm going to multiply it by 1/3. So I would have 1 squared is 1. 1 times 1/3 is 1/3. 0 squared is 0 times 1/3 is still 0. And then I'm going to have this repeating y value because of this symmetry. So let's go ahead and graph this. Let's start with the 0, 0. Okay, I still have that vertex here of 0, 0. And then I'm going to plot the point 1, 1/3. So you just have to do your best to be 1/3 of the way up that square. And then symmetry is going to put a point on the other side. I've got the point 2, 4/3. So 4/3 is about 1 1/3. Okay, so again, about 1/3 of the way up that square. And then I have 3, 3. And so symmetry is going to put -3, 3. I'm going to go ahead and connect that with a nice smooth curve. I'm going to label this the h function. Okay. Boy, I'm still being bolstered down or held down by that 0, 0. So 9 says, what do all 3 graphs have in common? Well, they all have the same vertex. And that vertex is 0, 0. So that there was no shifting. There was no moving up or down or left or right because that vertex is still in the same spot. I also noticed that they all open upwards, or they point upwards, okay? But to me, this H graph looks like it's wider, okay, than the parent function. It looks like it's kind of being pushed down a little bit, right? If I go to this point at 2, 4, it looks like that y value got pushed down, whereas the 3 made my y value get pulled up, okay? And so 10 says, how does multiplying the parent function by 3 change the graph? Well, that's my red graph to my blue graph. So to me, my graph looks skinnier. So my graph is more narrow. And it looks like my graph is being pulled upward. I'm going to say pulled, not shifted, pulled upward. And what that means is that I have a vertical means up and down, right? Stretch. My graph is being stretched out. Think of a rubber band. If I were to take a rubber band and pull on that rubber band is going to stretch out and become skinnier. 11 says, how does multiplying the parent function by 1/3 change the graph? Well, again, I still have 0, 0, but to me, this graph looks wider. It's wider than the parent function. And to me, this graph looks like it's being pushed down or pushed to the x-axis. In fact, we call that a vertical compression. Compression means to be pushed, to compress. If I push down on a rubber band, it's going to get fatter or wider, okay? All right, so I have these stretches that could happen. I have these compressions that could happen. We have shift up, shift down, shift left, shift right. What else could there be? But wait, there's more. There is more. There's one more idea, okay? So it says complete the table of values for f of x equals x squared and r of x equals -x squared. All right, so f of x equals x squared, that's our parent function. -3 squared is 9, -2 squared is 4, 1, 0, 1, 4, 9. That feels reasonable. This should say that I'm going to graph. It didn't, but I will. So I'm going to graph. I've got 0, 0. I've got 1, 1. I've got 2, 4, -2, 4. I've got 3, 9. So there's my parent function. And now I'm going to calculate -x squared. So let's try this. We've got -3 squared, but then I'm going to have that extra negative. See this extra negative on the outside? Okay. So -3 squared gives me 9, but I have this extra negative out front. So actually I'm going to end up with a -9. Let's try another one. Negative, and then in parentheses, -2 squared. So -2 squared is 4, but I have this extra negative on the outside of my function, so I actually get -4. In fact, each of these original y values are just going to get negated. So -1, well, I can't negate 0, so 0, and then -1, -4, -9. So I'm going to go ahead and graph these points. We still have 0, 0. But this time I have -1, -1, and 1, -1. And this time I have 2, -4, and -2, -4. And I have 3, -9, and -3, -9. I'm going to connect those points. Okay. And so it turns out that this very last step, this very last transformation that I could make is I could flip my parabola upside down. Okay, so it says describe how the graph of r of x compares to the parent function. Well, this graph is flipped upside down. Okay, or we could say it opens downward instead of opening up, so it opens down. Okay, and what this really means is that we have reflected. This is a reflection. And we have reflected over the x-axis is the official math terminology. So I have flipped it over the x-axis, which is why it looks like it has been flipped upside down. Okay, so we have lots of different things that we can do to change the look of the original parent function. And so we're going to take some notes on those different things. And then your job will be to put all those different things together and give it a try on your own. Okay, so some quick notes. The parent function of a quadratic which, recall, is y equals x squared, can be transformed in many ways. All right, so we're going to go through all the different ways that this parent function can be transformed, okay? And so I can take this parent function, y equals x squared, and I could add some number to it. I'll call that k. Or I can take that parent function, y equals x squared, and I can subtract some number from it. I'll call that number k. If I add a number to x squared, I'm going to shift up k units. And if I subtract a number from the parent function, I'm going to shift down k units. And when I say shift down k units, what I mean is if it says x squared plus 3, I'm moving up 3 units. So k represents whatever number I could, plug in for that. If it says y equals x squared minus 10, I'm going to shift down 10 units. Okay. Other things I can do is I can shift left or right. And so if we have y equals, remember the shift left or right though comes from being inside parentheses. So let's say I have y equals x minus, we're going to call this h. So instead of k, we're going to say h squared then on the outside. Or I could have y equals, in parentheses, x plus h, and then squared. And so remember, though, that when I'm in those parentheses, it is not what you think it is. X minus h does not mean I move left where the negatives are. It actually means I'm going to move right. So it's the opposite of what you think. Okay, so this means I'm going to move to the right k units. Whereas x plus h means I'm going to do the opposite, and I'm going to move to the left. I'm going to draw my arrow to the left. I'm going to move to the left k units. Okay, the opposite of what, or not k, I apologize. Move to the right h units and move to the left h units. My apologies. There's a couple other things that we can do. So bear with me as I run out of room here. Something else we can do is we can have y equals, and we could put a negative in front of our x squared. And we put a negative in front of our x squared. That tells me that I can turn my parabola upside down, okay? So that means we're going to be upside down. And in math, we call that a reflection. We're going to reflect over the x-axis. Okay, we turn it upside down. And the last thing that we can do is we can stretch my graph, make it narrower, or we can compress my graph, make it wider. So that happens when we add a coefficient to x squared. And depending on that number in front of x squared, that coefficient, depending on that number, I'm either going to stretch and become narrower, or I'm going to compress and become wider. And so if that A value is bigger than 1, I'm going to stretch. And if that A value is less than 1, or bigger than 0, so it has to be, did not mean to write equal to. It has to be positive, in other words, okay? It has to be a positive A value. So if I have a positive A value that's less than 1, then it's going to be a compress. Okay, and a stretch means I get narrower, and a compress means I get wider. So stretch, narrow, and compress, wide. Okay. So your job is to try the check your understanding. You can see in problem 1, we're tossing a couple of these transformations. Transformation just means a change. We are tossing a couple of these transformations together in one problem. We're going to ask you to graph that. I would use Desmos to graph that. Use Desmos, okay, to help you with that. And then in problem 2, you're going to take a look at those transformations and match them to the graphs. And then in 3, you're going to explain how you know if a parabola is going to open up or down. So give those a try, ask questions, and then you can try the 7-3 practice.